Hello, in this video I'm going to help you understand sort of how to manipulate equations and their equilibrium constants, not just to take a particular reaction and manipulate it one at a time, which is often very handy, but also to take several reactions and combine them together and to combine their Keq constants or the Kc constants, or really any sort of equilibrium constant value of K. You can manipulate reactions and combine their K values to make an overall reaction, much in the same way as we do with Hess's law when we're studying thermodynamics. So just a few kind of basic step-by-steps for this and rules for this. We're going to look at, I'm going to take you through some examples and some going through just here some real simple examples for the different manipulations that we can do, and then I'll take you through an example on the practice assignment that hopefully you picked up a copy of in class. If not, you can just write the equations down as I show them to you here in a minute on the homework page, and just follow along with those examples in your notebook if you have to. So one of the ways that we can manipulate a reaction equation is by reversing it or flipping it. So making the products the reactants and the reactants the products. So here on this first example, you see that sulfur dioxide is decomposing into sulfur and oxygen. That's on the black equation here, or what I'm calling reaction 1. All gases, oh, I'm sorry, not all gases, but gas, solid, and gas. In any case, we're not looking at the expression here so much as we're looking at they've given us a K value of 6.61 for that reaction. And so below it in red, you see that the same equation is given, but then flipped. So reactants are now products, products are reactants, sulfur and oxygen are becoming sulfur dioxide. So they've flipped it. How do we then find the K value for that reaction just having flipped it over? Well, if you think about the K expression would be the reciprocal of the original K expression. The products that were on the top will now be the reactants on the bottom, and the reactants on the bottom will now be the products on the top. So our K expression up here would have been, since we're leaving the solid out, would have been oxygen over sulfur dioxide. And if we're working with those as concentrations, then we'd have it in brackets like so. For the bottom reaction, we'd have the same sort of idea, but K would be instead now sulfur dioxide as the product on the top and oxygen as the reactant on the bottom. So without having to rewrite the K expressions for these, our first K would be oxygen over sulfur dioxide, and our second would be the reciprocal. Without even having to write that out, we hopefully can recognize that by flipping the reaction, we've created a reciprocal K expression. Therefore, if we know the K value for the first reaction, and we do, 6.61, we just find the K value for the second as the reciprocal of that, as 1 over 6.61. Punch that in your calculator and you got your answer here. The K value for our second equation is 0.151. Really pretty simple. There's nothing magical about that. It's just the idea of what a reciprocal is. And if you know how to set up a K expression, then that should be pretty straightforward. As we look at the second kind of manipulation, this is basically when we want to change the coefficients by some multiple. So as we look at the original equation that we had on the last slide, where SO2 is decomposing into sulfur and oxygen, the only difference between that and the second equation on the page here is that we're doubling all the coefficients. So we've doubled up all the quantities, the moles. So instead of 1 mole of SO2 decomposing, we have 2. And then of course we have 2 moles of everything in the output as well. Well, if you think about the K expressions for those, all we've really done is we've doubled all the coefficients, so we'd be squaring all the concentrations. And so in our first one, our K expression, again, leaving out sulfur as a solid, we would have oxygen, as in the last slide, over sulfur dioxide. For the second reaction, our K expression would be very similar. We would have oxygen on the top, we would have sulfur dioxide on the bottom. But because we've doubled the coefficients, we would also be squaring each of those concentrations. So if we compare K1 and K2, K2 is simply K1 squared, right? We've taken the same exact concentrations and squared them. And so as you see here, K2, our second equilibrium concentration, or rather equilibrium constant, is going to be the same as the first one, but squared. So to calculate that, we just take 6.61, which is our given K value for the first equation, and we'd square it, so 43.7. So for any multiple, you can take your original K value to that power. If you have to triple the coefficients, you simply cube it, and so forth and so on. So any kind of manipulation, and of course we have to be changing all the coefficients by the same amount anyway, because that would keep the equation balanced. We wouldn't just be doubling, say, sulfur dioxide, but not doubling everything else. So as we work through these, the coefficients sort of just naturally have to double, and with that, the power has to be changed by to that same degree. So double the coefficients, then you square the original K. And on the flip side of that is the other sort of manipulation if we reduce the coefficients. And so we see here that we've taken that same reaction, sulfur dioxide decomposing. And instead of doubling the coefficients, I've cut them in half. Well, the same idea then mathematically would apply. The K expression would simply be raised to the same thing that you've done, to the same power of those coefficient changes that you made. And so while K up here would be oxygen over sulfur dioxide, as in our original expression, down here, K for our second reaction would be oxygen over sulfur dioxide. But instead of squaring them like in the last situation, we're taking them to the 1/2 power, which of course is a square root operation in our math. And so when we reduce the powers by a fraction, we find the same root of our original K value. So K2 here will be the square root of our original K1 value, which, as we show down here at the bottom, punch that into our calculator, the square root of 6.61 is 2.57. So we can manipulate any reaction in that way, and we can do that with any kind of funky powers. We don't have to have even just simple square roots. As you'll see in some of the problems that you may have to encounter, you might even be changing the coefficients by weird things like 2/3. And in doing that, you can always just take in your calculator and raise things to the power of 2/3 instead of trying to find a funky root, a 3/2 root or something like that. You punch it in as a power. So keeping in mind that whatever you need to do in terms of the coefficient change, you can put in as a K to the 1/2 power instead of having to do it as a square root or a third root. Just take it to the 1/3 power for a cubed root and so forth. And I think you guys are pretty comfortable with that. So in a nutshell, here are the three manipulations. Flipping the equation causes us to find the reciprocal of K. Multiplying the coefficients by 2 or 3 or any other whole number typically would cause us to take K to that power. So here K squared or K cubed. And then reducing the coefficients in the equation by some fraction causes us to find that nth root of the original K value. So here having it, dividing the coefficients by 3 gives us a cubic root, or as I mentioned in the last one, again, a weird one, multiplying the coefficients by 2/3, which sounds really unusual, but happens occasionally, would cause us to take K and raise it to the 2/3 power. So just kind of getting comfortable with the math on that. Many of you haven't done these kind of weird roots in a while, and you've maybe forgotten the little nuances of how you punch those in your calculator. So that's why practicing them at this point is so important. If you've moved on in your life of mathematics to calculus and so on, you might not be doing this as much as you used to, and so just to kind of refresh you on sort of how some of those things are going to look. So let's look at some examples. Let's look at some examples on the assignment that you picked up hopefully in class. And again, if you didn't get this assignment, just write down the equations that you see, then pause this if you need to and write the equations down. But hopefully you have this page. I'm not going to start with the first one because I don't want to do multiple operations right away, but if you wouldn't mind, we're going to start with, this is the fourth one on that first page. And the idea is that these look, and I think you guys sort of even comment on it as you pick this up, that looks like Hess's law problems, where you're given these little equations and you're asked to combine them to make that overall bold-faced equation at the top by manipulating the equations that you're given. And we did this a lot with Hess's law, and you guys kind of crushed that. So hopefully you'll still have the same kind of confidence as we work with these, just in recognizing and how to flip the reactions, manipulate the reactions, and get what you need. So how to do that, again, it's sort of up to you how you want to tackle it, but I just kind of work my way left to right through the bold-faced equation and find a reaction that will give me what I need. So in this case, I'm going to start here and say that to get 2 CO2s on the left, I'm going to use this first equation, which has CO2 on the left already, and that sounds like a good place to be. I'm going to take that equation and I'm going to double it, because that equation has CO2 on the left, but I need 2 CO2s on the left. So I'm going to double that first equation and write it down here. 2 CO2s, oops, forming by decomposition here, 2 carbons. And it does say graphite. There isn't any other form of carbon in this equation, or any of the other equations, so I'm not going to write graphite again. If there were other forms of carbon, then I would definitely want to make sure to write that down and keep track, but I'm going to be a little shorter in my work here, just to make sure that I can get everything canceled out right. So doubling that first equation would double everything, and since the K value for that was 3.13, in doubling it, our K value now will be 3.13, but squared. Okay. And then that gets us CO2 on the left. It also gets us 2 oxygens on the right. So we've kind of covered that part of our reaction equation, potentially. Let's find something then that gets 2 waters on the left side of our equation. Well, I see that the second equation, as I'm giving it right there, has 2 waters right here on the left side. So I'm going to go ahead and just use that one exactly as it is. So I'm going to rewrite it though, just for the purposes of sort of staying organized. I'll go ahead and rewrite my equation and bring its K value down. So 2 waters becoming 2 hydrogens and an oxygen. No changes at all. So my K value stays exactly the same, 0.208. And then the last one is going to be important because we need to get our CH3COOH, our acetic acid. We need to get that on the left side of the equation. So to get that over here, I'm going to need to take that, on the right side of the equation from the left side. I'm going to need to take that last equation there that I'm marking up here in green, and I'm going to need to flip that one. In order to get the CH3COOH on the other side, on the product side, I'll have to flip that one. So I'm going to go ahead and rewrite it that way. 2 carbons on the left now, if I flip it, 2 hydrogens on the left, and an oxygen on the left will form, according to this reaction, our CH3COOH, and exactly in the right quantities, hopefully here. Okay. And because I flipped it, I need to take the reciprocal of that K value, so I'm going to write that as 1 over 1.56. And there I've got my equation, hopefully, with all the pieces in the right place. I'm just going to go through and make sure that the right things cancel out. Right? We're going to want CO2 on the left. We've got it. We're going to want water on the left. We've got it. We're going to want CH3COOH on the right. And we've got it. But let's make sure everything else cancels out. So here 2 carbons would cancel 2 carbons. We've got a winner there. 2 hydrogens on the left, 2 on the right. That cancels out. And then our oxygens, we do want these 2 on the right. We're going to need those in our overall reaction. But beyond that, we have these other oxygens that would cancel. So those would go away. And sure enough, it leaves us with exactly what we want. So we've got just the right pieces in just the right places. To get our overall K then, we don't, as with Hess's law, add these together. We need to take the individual Ks that we've manipulated, at least a couple of them we've manipulated, and we need to just simply multiply all these together. So go into your calculator, just punch all these individual pieces multiplied next to each other. So 3.13 squared times 0.208 times, and you can punch it in however you want, 1 over 1.56. That would work if you punch it in like that. Or if you're comfortable with just using that reciprocal button on your calculator, you might punch it in as 1.56 raised to the -1 power. Whatever works for you in your calculator is fine. But as you punch that in, and you should make sure to do it at this point, make sure you do, it should give us an overall K value of 1.31. So when we punch all that into our calculator together, we multiply those individual K terms together, not adding them together. A lot of multiplication and division when it comes to K expressions, because everything is set up in the original K values, everything is set up as multiplication and division. So there really isn't any addition or subtraction when it comes to handling the K values at the end. That's the idea with that. So let's look at another example. Let's go back to the top one now, because there is a multi-step manipulation in this one, and I want to show you how to handle that too. We can totally do that. We can do more than one manipulation at a time. So in this first one, I want to get CO2 on the left, carbon dioxide, decomposing into carbon and oxygen. So I'm going to look through my reactions here and see if I can find the one that'll get me CO2 on the left. Well, there's only one reaction that has CO2 in it, and it's right here. But I need it on the left, so I'm going to need to take that middle equation of my 3, and I'm going to need to flip that one to get carbon dioxide as a reactant. So I'll go ahead and do that. CO2 and 2 waters, making CH4 and 2 oxygens. And so if I flip that, again, my middle equation here, I'm going to take that 5.94 and do the reciprocal of it. So 1 over 5.94. That gets our CO2 as a reactant. Okay. The next thing to recognize is we need to have carbon. I can see I need to have carbon here as a product. And fortunately, we've got a reaction that already has that. So it's the third one that has carbon as a product. So I'm just going to use that one exactly as is. I'll go ahead and rewrite it though, just to kind of keep my things down here for later, so that I can cancel them out and double check my work. Some of you I know are really happy with keeping those arrows lined up to kind of keep your sanity. I don't blame you on that one. Oops, sorry about that. Feel free to stick with that plan of lining up your arrows. We kind of did that with Hess's law in order to keep ourselves aligned and cancel things more effectively. So we're using that bottom equation just exactly as is, which means we'll use its K value exactly as is, 0.154. And that gets us our carbon as a product. So our last piece is we need to get oxygen in there someplace and get 1 oxygen on the right-hand side. So I might look at these and think, well, how am I going to I've already got oxygen on the right-hand side in that first reaction equation, right? If I see it up here as a product already, but I've got two of them on that right-hand side, and I don't need two of them on the right-hand side. I only need one to match my original equation. So you might recognize, well, that's not quite working out. I need to get rid of one of those oxygens. I might also look at it and say I don't need the water on the reactant side that I have in this first reaction. So I need something that's going to have water on the right-hand side in order to cancel that water out. And if I look at my equation options, I've got my first one left. That's got water, but it's got it on the left-hand side. So I'm going to need to flip this reaction in order to get water as a product, right? I'll go ahead and do that. I'm going to flip that reaction. It's going to give me water as a product. And it's going to have hydrogen and 1/2 of an oxygen as reactants. Now I look at that and say, I flipped it. So that kind of covers it. But I've got two waters in that original reaction up here. I've got two waters on the reactant side, and I only got one as I've flipped my original reaction now. So I need to flip it to get water on the product side, but I also need to double it. So I'm going to flip and I'm going to double that first reaction equation. And I can do both of those things. So go ahead and go through here and do that. I'm going to change this to a 2. I'm going to go ahead and change my oxygen, to a 1 because I doubled it. And I'm going to double my water. So I've flipped and doubled the coefficients on that first reaction equation in the one that I've written here in green. So in doing that, we have to also then alter our K value in both of those ways. So I'm going to take my 0.192 and do the reciprocal because I flipped the reaction equation. And then I also need to square that term. So flip it and double it means reciprocal and square it with the original K values. So if we go through now again and double check that things cancel out the way that they ought to, our two waters will cancel out the way that we're hoping. Our two hydrogens will cancel out because we don't need them, right, in our reaction eventually here. And our methane, CH4, will also cancel out. Make sure we're good where we are. Notice again, we have CO2 on the left. We got that one left over. We got carbon as a product. That works out. We've still got one oxygen on the left and two on the right. So basically, we're going to cancel out this oxygen with one of these oxygens that were there in that first reaction as we used it. And so that leaves us with exactly what we need, our one oxygen as a product. So just kind of going through and in the chaos of all this flipping and canceling, make sure that you have what you think you have. And it's exactly what we need here. So again, lastly, we'll take all three of these terms and we'll multiply those together in our calculator rather than adding or subtracting. So multiply all those together, and in the end, we should end up with a K value of 0.703 for that. So that's kind of the idea on these. There really isn't on any of the rest of the ones that are in this assignment at all anything that's too novel compared to that. We should maybe take one more, and if you understand what this is all about, you kind of feel like you've got a sense of it, then you don't have to follow along with us any further. I guess I'll show you one more that has some funky stuff going on in it, so that you can see maybe as tricky as they might get how that would look. So this is actually, I believe, on page 3. If you're following along here on the assignment, it's the one that has iron and carbon dioxide reacting as the reactants in our reaction here. So iron and carbon dioxide here, that's this one here, at the bottom of page 3. There's a lot of iron, there's a lot of carbon, there's a lot of oxygen. If you scan over those equations, there's a lot going on. And so just to kind of keep your wits about you, be really cautious on these when there's a lot of the same things. It's easy to kind of get lost in the flurry. You end up sort of looking like a lion chasing a zebra in the crowd, and your eyes get all bugged out here. So let's take it kind of carefully, and I'm going to just do what I did before. 2 irons on the left. I need 2 irons on the left. And again, in all this chaos, there's only one reaction that has iron at all, and it's this last one. So iron by itself, that last equation, but I'm going to need 2 irons. All right, so I'm going to go ahead and use that equation, but I'm going to double it. So I'm going to take that down here and write it. 2 irons, 2 CO2s, forming 2 FeOs, or iron oxide, and 2 carbon monoxides. Because we doubled our original equation, we're going to take that K value, which was 0.117, and we're going to square it. So we've covered our iron, got that taken care of. We've actually also taken care of 2 of our carbon dioxides that we need in that eventual reaction. So we have 2 of these sort of accounted for, but not the third one, so that'll have to come from somewhere else, right? what else can we pull out of these and use for some of these? Well, I'm gonna look for something that I don't have covered yet, and that is I need iron oxide, Fe2O3. I need that as a product. And there's only one reaction that has iron oxide in it, and it's this first one, right? We have iron oxide right there. But that one has 3 iron oxides as a product, and I only need 1, right? So I'm going to take that first equation, the one that I'm marking up here in blue. I'm going to use it. I'm not going to flip it, but I am going to take it by 1/3 of its size. So I don't need 3 iron oxides coming out of that. I only need 1. So I'm going to take this down by 1/3 and take the recipe down, or take the proportions downward instead of upward. So we haven't done anything like this yet. So let's run through this one. And to do that, then I'm going to have to manipulate these coefficients and everything by 1/3. So we're multiplying, basically distributing 1/3 to all those coefficients. So 1/3 times this 2 will give me 2/3 of a mole of Fe3O4. If I multiply that, distribute that to my carbon dioxide, I'll have 1/3 of a mole of carbon dioxide. At this point, you're like, gross, fractions, ick. Yeah, it'll fix itself up. Just hang on. If I distribute that 1/3 to the Fe2O3, which was our whole intent in the first place, now I get the 1 mole of Fe2O3. And if you like to go ahead and put 1s in, that's not a bad idea. And then, like with the carbon dioxide, I'm going to distribute that to my carbon monoxide. That's going to give me 1/3 of a mole of carbon monoxide as well. Now, I've taken that coefficient, or rather that K value, pardon me, of 0.114, and I'm going to take it to the 1/3 power, which is like the cubic root. So whichever one you prefer, you can write it as cubic root of that, or write it as raising it to the 1/3 power. And that takes care of our iron. So, well, putting these pieces together, if I've got one equation left to work with, it must be necessary to use it somewhere in this equation, and I just have to figure out exactly how. And you can kind of grab on here wherever it makes sense to you. It's sort of like climbing a rock wall. You don't all have to take the same path upward. Whichever handhold looks like the best one for you next, you should just use that one. I'm going to grab onto this Fe3O4 handhold and recognize that in my equation that we just wrote, the blue one, right? I don't want this Fe3O4 to last, right? I want this Fe3O4 to get out of here, because that doesn't need to show up on my eventual equation. And so to get that, I can sort of look at that equation that we've just written and see that to get 2/3 of an Fe3O4 to cancel out, I'm going to need 2/3 of an Fe3O4 on the other side. And so it's okay to do this. Take your last equation here, and instead of trying to figure out what to do with it from the start, just kind of in advance forecast what it's going to need to look like. And that is, I'm going to need to have 2/3 of a mole of Fe3O4 on this side. If I'm going to make this work, those will cancel out, right? That will cancel with the blue one that I circled there. So how will I get that? How will I get the middle equation of my list from the original list here to put 2/3 of a mole of Fe3O4 on the other side of the equation? Well, it's not simple, I guess. It is simple, but it's not something that we've done. We're going to need to take that equation, that middle one, we're going to need to flip it to get the Fe3O4 on the other side. And we're going to need to take it times 2/3 of its original size. So we're flipping it and we're 2/3ing it, if that's such a verb. So I'm going to do that. Flipping it and 2/3ing it. So I've already taken the Fe3O4. I'm going to do the same thing with my CO. If I flip CO to this side and distribute the 2/3, I'll have 2/3 of a mole of carbon monoxide. And on the other side of my reaction, if I take 2/3 times 3, right, that'll give me 2 moles of FeO. And 2/3 times my carbon monoxide, that'll give me 2/3 of a mole of carbon dioxide. So I've taken that equation, I've inverted it, and I've taken all the coefficients times 2/3. So down here I need to take the 7.92, which was its original K value, invert it, so that's reciprocal, and then take that whole thing to the 2/3 power. So you got to be kind of careful punching this into your calculator. It's not complicated math, but it is where you have to be very careful you don't goof up a keystroke in your calculator to do that. Now let's just go back and make sure that in all this insanity we've got just what we need in terms of all the parts, right? We do want the 2 irons to be on the left, and there they are. Okay. We've got 2 carbon dioxides from that first equation, and then in the next couple of equations we have 2/3 and 1/3. So all this together gives us exactly what we needed, 3 CO2s. So they're working together for sure on that one. All right. We've got our Fe2O3 that we needed, our iron 3 oxide as a product. We have 1 mole, so that's a check. And then like on the carbon dioxide, if we put all these together, we've got 3 moles of carbon monoxide to match up with what's up there. So we've got all the right pieces, but does everything else cancel out? Let's make sure. 2 iron oxides, 2 iron 2 oxides cancel out there. And then 2/3 of a mole of our Fe3O4 cancel out. And so sure enough, everything worked out. So there's some real kind of delicate manipulation that goes on in that one, but it works. Go to your calculator, punch this bugger in at the end. All that together in my calculator should give me a final overall result when I multiply those together with all those powers and stuff of 0.00167. So that's kind of a look at a more complicated manipulation of K values on that last one. I don't believe there are any others on this whole assignment that are quite as messy as that one. So take your time with them. There are some where you'll have to do some fractional powers, and there's one where you have to go as much as raising it to the power of 4. So don't be afraid of doing that. You can do anything that makes it work, and your calculator can handle it. So try a few more of these out. Work on the rest of them. If you don't need to be working on any of the other problems that we've been working on lately, then work on the rest of these. Take a few today, take a few the next day, spread them out if you wish, but be able to handle these. I would say that generally speaking, if you can do these, you'll be all set for the ones that you might run into when it comes time to do it on an actual test. All right. Thanks for listening, and if you have questions, see me soon. Talk to you then.